Section 3.5, and we're going to talk about the triangle sum theorem, and it comes from, I'm going to put in parentheses, the parallel postulate. So the parallel postulate says, and first let's remember, what is a postulate? Something that we accept as true without proof. So our parallel postulate. Our parallel postulate says that if we have a line, if we're given a line, and a point that's not on the line, so we're in the plane here, we're not in space, we're in the plane. So given a line and a point not on the line, there is exactly one line that goes through that point that is parallel to the other line. And picture's pretty easy here. Here's our line. Here's our point P. The parallel postulate says that there's exactly one line through P that's parallel to L. And the parallel postulate, it's one of the most important postulates. It's kind of, how do I want to say it? It's really the foundation, almost, of plane geometry. And for a long time there's been argument about the parallel postulate, that we should be able to prove the parallel postulate as a theorem. And then there's other types of geometry come from saying the parallel postulate isn't true. So through a point not on a line, there are an infinite number of lines parallel to this line. Or there are no lines through this point that are parallel to this kind of line. So we end up with different kinds of geometry. So on the surface of a sphere, there are lines that we can draw through this point on the surface of a sphere are always going to intersect this other line. So if we think of this point being at the North Pole and this line being the equator, any line that we draw through the North Pole hits the equator. And then if we talk about an infinite number or no lines being parallel, then we end up with a different kind of geometry. So not accepting the parallel postulate or thinking about the parallel postulate in a different way leads us to different places in math. So it's the parallel postulate leads to all kinds of different kinds of geometry than plane geometry. So for plane geometry, the parallel postulate is really what makes it plane geometry. If we say the parallel postulate isn't true, it leads us to other kinds of geometry, which are really a pretty modern invention. These other types of geometry. So the parallel postulate says through this point there's exactly one line that's parallel to this line L. And this leads us to the triangle sum theorem, and we'll talk about how they're connected. So the triangle sum theorem. This is something that we've known for a long, long, long time. We've used it in our math classes for probably since elementary school. The triangle sum theorem says that all the angles, the measures of all the angles in a triangle add up to 180. So the sum of the measures of angles in a triangle is 180 degrees. And it turns out, I've mentioned these other kinds of geometry on the surface of a sphere. If you make a triangle on the surface of a sphere and you add up the angles in a triangle on the surface of a sphere, they're more than 180. And other kinds of geometries, the sums add up to less than 180. And it depends on how the place where we're doing this geometry is curved. So parallel postulate works in a plane. The others have to do with places that are curved. So let's make a connection between the triangle sum theorem and the parallel postulate. And I have a little demonstration that shows that connection. So what I've done here is I made this red line is parallel to the bottom of this triangle. So no matter what I do to the triangle, no matter how I move it around, this red line stays parallel to the bottom of the triangle. And we're interested in what all of these angles add up to in the triangle. So here's our point, here's our line, here's our exactly one line that's parallel to this line. So what I'm going to do is I'm going to rotate this triangle around this point. If I'm selected this, it's going to rotate around this point. So I'm going to rotate. And I'll do it. So we do it 40. I'm going to do it 45 degrees at a time. So there's this triangle rotated about that point 45 degrees. So this angle, this little angle down here, is now up here. So let's rotate it again. So now this angle is rotated up to here. So I'm rotating that triangle around. Let's rotate it again. Now this angle is rotated up to here. What do you think is going to happen with that angle when I rotate this triangle all the way around? So we're looking at this angle. What do you think is going to end up? So Sam says it might be lined up with this red line. So let's rotate it 45 degrees one more time. So this triangle rotated around, and now it sits right in that space there. So let me color that. Let's color it red. So there's my red triangle that I've rotated around. So this angle rotates all the way around and touches right there. Let's do the same thing with the other side of this triangle. So I'm going to rotate it the other way. I'm going to go minus 45 degrees. And now this angle is rotated to here. So what do you think is going to happen with this angle now? Let's make a conjecture. What's our conjecture about where this angle is going to end up? Rotate it again. So where do we think it's going to end up? Right on the line. That's kind of what it looks like, right? Transform, rotate it again. There it is. So let's color that one. Color blue. Alright, so now this triangle is rotated around, this angle rotated up to here. this angle rotated up to here. What does this angle plus this angle plus this angle have to add up to? 180. This is one angle of the triangle. This is the other angle of the triangle. And this is the third angle of the triangle. So all three of the angles of the triangle line up onto this parallel line, so they have to add up to 180 degrees. So this kind of suggests how the parallel postulate and the triangle sum theorem are related. So let's prove that the angles in a triangle add up to 180 using what we know about parallel lines now. So this suggests why it works. So now let's do our proof. And finally, as sophomores in high school, we'll be able to prove something that we've used since we've been in elementary school. We'll be able to prove why it's true. And I think that's pretty cool. All right. So here's our proof. We're going to prove the triangle sum theorem. So we'll start with a triangle. And I'm going to call this angle 1. Go the other way. 1, 2, 3. And we'll call it triangle ABC. So we're going to be given triangle ABC. And we want to prove that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. Well, here's our first step in our proof. I'm going to draw the parallel line. So there's my parallel line through point C. I'm going to call that line L. So now we're set. So here are going to be my statements and my reasons. So my first statement is that line L is parallel to segment AB. What would be my reason here? How do we know that we can make that parallel line? The parallel postulate tells us we can do that. So my reason would be parallel postulate. It tells us we can make that parallel line. Well, let me label a couple of other angles, 4 and angle 5. What do measure of angle 1, 4, and 5 have to add up to? Measure of angle 1 plus a measure of angle 4 plus a measure of angle 5 equals 180. And they're not, we can't say they're a linear pair because there are 3 of them. I can just say that the angles form a line. I guess if we had a name for them, we could call them a linear triple. We don't have a special name. So they form a line. That's a good enough reason. All right. What kinds of angles? So this line L and this line segment AB are parallel. What kind of angles are angle 2 and 4? They're congruent, and what was their name? They're between the parallel lines, and they are on the opposite side of this side of the triangle. So alternate interior angles. So we know that the measure of angle 2 equals the measure of angle 4. because they are alternate interior angles. How about angles 3 and 5? They are also alternate interior angles. So measure of angle 3 equals measure of angle 5 for the same reason. And now I'm going to take measure of angle 3 and put it right here. And I'm going to take the measure of angle 2 and put it right here. Because it's the same as measure of angle 4. The measure of angle 3 is the same as measure of angle 5. So I can say measure of angle 1 plus a measure of angle 2 plus a measure of angle 3 equals 180. And what would my reason be there? Substitution. I substituted those in. And we've proved now, starting from the parallel postulate, we proved that the angles in a triangle have to add up to 180 degrees. And that's all there is to it. So now we know why all the angles in a triangle add up to 180 degrees. The reason is because the parallel postulate is true on a plane, or we accept that it's true. So kind of interesting, huh? This thing that we've accepted for almost as long as we've been in school, now we're able to prove it. All we had to do was know about the parallel postulate. Questions on the proof? Questions on the parallel postulate? All right, let's look at an example of how we might use the triangle sum theorem. So here's a triangle, and we want to find a bunch of missing information. So this is z degrees, this is y degrees, this is .36 degrees, this is 32 degrees, this is x degrees, and this is 46 degrees. We want to find x, y, and z. So how can we get started on this? What's going to be the easiest one to find first? What? X. Let's find x. Isn't this like what we did on the opener? We know that all three of the angles in this triangle have to add up to 180 degrees. So we know that x plus 32 plus 46 has to equal 180. So x plus 78 equals 180. Subtract 78, and x equals 102. So now I know that that's 102 degrees. What do these two have to add up to? What do x and y have to add up to? 180, because they are what kind of angles? They are linear pair. So y plus 102 equals 180. So y equals 78. Isn't this what we saw on the opener? That and that are the same. We'll talk about that in just a second. So x is 102, y is 78, and all the angles in this triangle have to add up to 180. So z plus 36 plus 78 has to equal 180. So z plus 104, is that right? 114, there we go. Equals 180. Subtract 114. And z finally equals 66 degrees. So x is 102, y is 78, and z is 66. So we use a triangle sum twice, and we used a linear pair once. Questions on that example? All right, let's talk about this this thing that we've seen here a couple of times, that this and this are the same. That is called the exterior angle theorem. So let me draw a picture, and we'll talk about some vocabulary. So I have a triangle. For this theorem, we have a triangle drawn kind of on a line here. And I'm going to call this 1, 2, 3, and 4. So we call angle 4 an exterior angle. And we call it an exterior angle because it's outside of the triangle. We call angle 1 and 2 are the remote interior angles. Remote just means it's far away. And interior means they're inside the triangle. So angle 1 and 2 are far away from angle 4, and they're inside the triangle, so we call them remote interior angles. The exterior angle theorem says that the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2. And if we said that in words, we would say the measure of an exterior angle is the sum means add, the sum of the measures of the remote interior angles. So that's what the exterior angle theorem tells us. And basically the idea is, and if we could sketch out a proof at this point, I'm not going to go through the proof right now, but just like we've done with our problems, we know that all three of these angles have to add up to 180. These two angles have to add up to 180. So angle 3 plus angle 4 has to be the same as angle 3 plus these two together. So these two together have to be the same as angle 4 by itself. But it all comes from all the angles in the triangle adding up to 180 degrees. So let's look at a couple of examples of how we would use the exterior angle theorem. So here's our picture. call this angle 1. This is 46 degrees. This is 41 degrees. And this problem says find measure of angle 1. Well, this is exactly like our opener. We could say we add these two together, we get this third angle, and we subtract that from 180 because these two are a linear pair. But now that we know the remote exterior, the exterior angle theorem, we know that the measure of angle 1 has to equal 46 degrees plus 41 degrees. So measure of angle 1 equals 87 degrees. If we couldn't remember that this works this way, we can always just add these together, find this third angle, and then say these two are a linear pair, so we subtract from 180. So we can do them just like we did the opener, and just like we did the last example that we talked about. Questions on that example? All right, let's look at another one. So this is 119 degrees. This is 53 degrees. And this is angle 2. We want the measure of angle 2. So if we don't remember this theorem, we can always go back to the way we would have solved the problem before. These two have to add up to 180, so we can figure out this angle. And then all three of the angles in the triangle have to add up to 180. So then we can find angle 2. If we remember the exterior angle theorem, we know that the measure of angle 2 plus the measure of angle 53 has to equal 119 degrees. Not measure of angle 53, just 53. So we can say that the measure of angle 2 is 119 minus 53, and we get that the measure of angle 2 is 66 degrees. And again, if we don't remember the theorem, we could always just find this angle and then add everything up and subtract from 180. So questions on the exterior angle theorem? Okay. Bottom line, all three of our angles in our triangle add up to 180. That comes from the parallel postulate. And exterior angle forms a linear pair with one of the angles in our triangle. So that lets us figure out exterior angles and our remote interior angles. Okay. Homework.